Before we proceed further with NMR, I thought I'll again do a brief recap of what we talked about previously. So, we know that when there is radio frequency radiation, there is certain types of atoms which have odd numbered neutrons or protons in their nuclei, which have a finite spin, and this finite spin actually can get altered by the absorption of radio frequency radiation, right. So, the energy state of this atom will increase when it absorbs the radio frequency radiation, and of course, conversely what can also happen is that by emission of the radiation, the energy state can come back to its ground state. Okay. So, you have energy transitions happening in the nuclei because of the spins, and that happens only in specific sets of nuclei which have odd numbered neutrons or protons or both. Now, we also saw the fact that when you place such type of nuclei in an external magnetic fields, the spinning protons which are there in the nuclei act like magnets. So, there is low or high energy configurations possible in this system, right. The low energy configuration is obviously more stable, the high energy configuration is unstable, right, in which case you are actually having a system that is not really stable when you have an external magnetic field that is applied to the spinning nucleus. Now, we saw that in certain cases the nuclei can be extremely shielded also. Why does this shielding occur? Because you have circulating electrons around the nuclei which are providing an environment which is separating the nucleus from the applied magnetic field. So, you have this separation or shielding which happens because of the circulating neutrons, and obviously elements or atoms which have a larger number of electrons will have greater extent of shielding around them, right. So, the magnetic strength must be increased for a shielded proton to flip at the same frequency, or for the absorption of the radiation to happen and flipping to happen at the same frequency. You need to then increase the strength of the magnetic field because of the shielding which actually happens. Now, we also saw that the resonance or frequency of the transition, the resonant frequency of a transition is related to a factor called the gyromagnetic ratio, which is unique for every type of atom. Okay. So, what you do is when you apply the external magnetic field to the system, the resonant frequencies at which radio frequencies are or radio frequency radiation is getting absorbed is given by this formula where frequency is equal to gamma h divided by 2 pi, where gamma is the gyromagnetic ratio which is specific to the type of element that is being analyzed, h is the strength of the magnetic field, right, and nu is the frequency. Now, when you present data related to NMR, it is usually presented in terms of the shift in the radiation or shift in the peak relative to the peak which is offered by a reference material. In this case, the reference material used is tetramethylsilane, which is generally unreactive with other organic compounds and gives absorption which is mostly shielded. So, most of the peaks associated with TMS will be towards the location where you have more shielding, whereas the other atoms that are present which are generating the peaks may be present either to the left or to the right of the TMS peak. So, when you present it in this type of a shift type pattern, so what would be the delta shift for TMS itself? Since it is a reference material, delta will be 0. So, when you present this information of NMR or absorption of radio frequency radiation by different types of atoms in a species, you actually will generate an NMR pattern which will look somewhat in this way. So, you will be plotting the intensities or the resonant frequencies at which the radiation is getting absorbed with respect to the location. The location is determined by the chemical shift. Now, chemical shift, because we are multiplying it by 10 to the power 6 here, right, we actually measure the chemical shift in terms of parts per million, ppm, okay, and that is what you will see most NMR patterns being represented as. I will come back to that in just a minute, but before that, of course, we also had an overview of a typical NMR spectrometer in which you have the sample which is in a liquid state which is actually subjected to this external magnetic field, and then you have the radio frequency radiation which is transmitted through the sample, you have the absorption taking place, and then the detector actually detects the RF radiation that comes out of the sample, right, and you will actually be able to figure out at what frequencies did the absorption actually take place, and this is your diffractogram or your pattern which is obtained at the result as a result of your experiment. Okay. So, now of course, this in this example the pattern is drawn with respect to the strength of the magnetic field, but you can convert the magnetic field as I showed you earlier into a frequency, and the frequency can be converted to the shift. Okay. Now, again you can do this experiment in several ways. One is you keep the external magnetic field strength constant and vary the frequency of radiation to see the absorption. Alternatively, you can keep the radio frequency constant and vary the strength of the magnetic field. Okay. So, that would be the two ways of actually operating this instrument, and modern instruments can actually do multiple frequencies at once and resolve all of them using a Fourier transform, just like we looked at with infrared spectroscopy. Okay. So, now the NMR signals or the peaks that you get at different locations, that means with respect to different chemical shift delta, the number of signals show how many different types or kinds of protons are present, right. You may have different kinds of protons within the same sample like silicon, aluminum and so on and so forth, right. The location of the signal shows how shielded or de-shielded the proton is. Now, more the shielding, where will the delta value go when higher shielding is there? Towards 0, or even to the right of 0, that means in the negative regime. Okay. So, we plot the delta 0 here, negative is in this direction and the positive is in this direction. So, this is less shielded and this is more shielded. I will show you again this pattern and representation in just a minute. So, the location of the signal shows how shielded or de-shielded the proton is. The intensity of the signal shows the number of protons of that type. Okay. For example, if you are getting silica which is in the dual state, that means there are two silica tetrahedra joined together, right. So, that is called a disilicate. So, that will have a specific location of the peak or specific chemical shift at which you detect that peak, and the intensity of that peak will tell you how much of the disilicates are present in your system. Okay. The signal splitting shows the number of protons on adjacent atoms. In a molecule, if you have protons on adjacent atoms that are both being subjected to this nuclear transition, then the peak itself may show a splitting type of a behavior, and that indicates the number of protons on adjacent atoms that are creating these interactions next to each other. Okay. I will show you some examples. So, of course, the NMR plot, as I said, you plot against the delta or the shift. Okay. The more closer to 0 you are, the more shielded the material is. The closer to 0 you are in the increased shielding direction. You can also go towards negative directions. Negative means what? If you look at this formula once again, negative simply means the frequency of the sample is lesser than the frequency of the reference, lesser than the frequency of reference. Positive implies frequency of sample is more than frequency of reference. Okay. Okay. So, generally in a sample, if you have more electronegative atoms, there is a lot more de-shielding and that generates a greater shift. Just an example was given here previously of methane, and as you increase the level of substitution of hydrogen by chloride or chlorine inside methane, you get increasing shift to the left. That means the electrons or the compound gets more and more de-shielded. So, you increase the chemical shift, that means you are going towards the left from 0 as you are getting more and more de-shielding because of electronegative atoms that are present in your material. Now, in some cases when we want to use solid samples, okay, you can actually use a technique called magic angle spinning, MAS. There we actually
spin the sample at a range of frequencies between 1 and 130 kilohertz at the magic angle theta m, which is about 54.7, right, which corresponds to a cos square theta of 1 by 3. With respect to the direction of magnetic field, what we essentially do by doing so is we make the broad lines of radiation much narrower, and we are able to identify much better and analyze the spectrum in solid state NMR, nuclear magnetic resonance. So, typically when we do silicon or aluminum type of detection in nuclear magnetic resonance, typically for identification of the types of CSH that are present in your cementitious systems, we opt for solid state NMR with magic angle spinning experiments. Now, just to give you an example of how relevant NMR is to identify the state of the CSH present in our cementitious systems. So, generally for silicon we have a frequency of 59.59 megahertz, which corresponds to a magnetic field of 11.72 Tesla, and for aluminum it is 130.4 megahertz, which is typically used. Because why do we want to detect silicon and aluminum? Because these are principal components that are present in your CSH. Okay. Now, when you use a software associated with the NMR spectrometer, it allows several NMR spectra to be decomposed simultaneously using the same spectral parameters. So, you actually get an analysis of each individual component across the entire collected data. And what we want to do is fix the relative intensity to agree with the proportion of corresponding sites. So, what we have to come up with first is a structural model of the material that we are trying to analyze, and based on that structural model we fix the maximum limits for certain components or fix maximum relative intensities for the components. For silicon spectra, 29 silicon spectra, what we can do is choose each component. For example, if you get a peak like this, each of these peaks can be deconvoluted or broken down into a mixture of wider peaks and sharper peaks. Okay, I will show you this deconvolution method later. So, each peak is broken down into a combination of wide peaks and sharp peaks. The wide peaks are basically your bell curves, Gaussian peaks. The sharper peaks are the Lorentzian curves, or those are the sharper functions which produce the intensities or produce the patterns which are looking much sharper and less broader as compared to the others. So, this is NMR spectra of CSH or calcium aluminosilicate hydrate, CaSH, at different water to cement ratios. So, this is the aluminum NMR spectra, 27 aluminum, right. So, here what you see are different states of the bonding in alumina. For instance, resonance is the region 70 to 55 ppm, 30 ppm and 2 to 5 ppm correspond to aluminum atoms in coordination of 4, 5 and 6 respectively. What do you mean by coordination number of an atom? The number of atoms that are right next to it or that are bonded right next to it. So, coordination state of 4 implies the aluminum is in a what state? Tetrahedral state, tetrahedral. 6 means octahedral state, and that is what we associate with commonly with alumina, is that alumina should be in octahedral state. So, at octahedral state you expect the shielding to be more or less, there will be greater shielding for higher coordination number, right. When you have a coordination number that is higher, you will get greater shielding, and when that happens your location of the aluminum peak is very close to 0, 2 to 5 ppm. So, this peak here in this aluminum spectra, NMR spectra, corresponds to the octahedral state of aluminum, whereas the peaks to the left of this, which are showing a greater shift or more deshielded values, right, you are getting alumina in other forms, octahedral and other coordination forms. So, that is what is being represented in this picture here with respect to the change in the alumina to silica ratio of the CaSH. You do get this octahedral coordination which seems to increase with higher level of alumina incorporated in the CSH. What does that mean with respect to cement chemistry? What does that mean? When will you increase the alumina content in the CSH? When you have more pozzolans in the system. like fly ash or slag, which bring in their own alumina which are reactive alumina, you actually will incorporate that into the structure of CSH. So, with that you will actually increase this octahedral coordination of your aluminum which is present in this system. You also see that you are actually changing the coordination which is in the other region, that is 55 to 70 region, which is the tetrahedral aluminum. So, you see that that is also increasing as you increase the alumina to silica ratio, right. So, with this you can actually track the growth of your CSH or the change in characteristic of the CSH with respect to first time, right, and then secondly with respect to the increasing degree of substitution of cement with pozzolanic additives. So, this NMR is actually a very strong technique which helps you determine these kinds of structural changes that are happening in your CSH. Now, this is a silicon magnetic angle spinning spectra. So, in silicon spectra the shift is to the negative side. You see here the axis is plotted to the negative side. Okay. So, just to come back once again to this representation of the shift here. So, the instrument typically has a specific frequency of operation 300 megahertz NMR instrument. So, in which case the frequency of TMS will be exactly 300 megahertz. The resonant frequency for TMS will be exactly 300 megahertz, that means the shift will be 0, right. So, corresponding to that shift location you now have deshielded atoms which are representing a shift which is on the positive side, whereas more shielded, highly shielded atoms are to the negative side. In the case of silica you will see that the shift is towards the negative side. Now, interestingly with silica you get different types of bonded states of silica. Now, in the simplest form, how does silica exist? In tetrahedral state, right. You have SiO4 tetrahedra, okay. That is actually a stable silica form on its own. Tetrahedral silica is a stable silica form on its own. You know that in quartz you have this tetrahedral silica which are arranged in a regular pattern. In glass you have the same tetrahedral silica, but they are arranged in a very disordered pattern, which makes quartz to be unreactive and glass to be reactive. So, now what happens is with increasing degree of reaction in a cementitious system, your tetrahedral silicate will start getting converted into other forms of silicates. For example, we know that structure of CSH is often told to be chain like or sheet like, in which case you start forming a greater degree of coordination for the silica tetrahedra. Okay. So, there are different states in which silica systems exist within the cement paste, and because of which you get multiple peaks given by NMR with respect to the type of silica that you are trying to observe. Now, I will show you this in much more clarity here. So, silica polymerization, the degree of silica polymerization is represented by these terms Q0, Q1, Q2 and Q3. Q0 corresponds to the simple tetrahedral state of silica, and that has a peak in this range of about -60 to about -80 ppm. As you move more and more from Q0 to Q4, as expected, the amount of shielding, what happens to the amount of shielding? It increases, right. So, it becomes more and more negative with respect to TMS, and you get the Q4 tetrahedra, Q4 type of silica, which is basically framework or tectosilicates. Okay. When you form a framework, that means you have a 3-dimensional coordination of the silica tetrahedra, those are tectosilicates, and that you see a Q4 type of a system. At the smaller end you have the orthosilicates Q0, which is simple tetrahedra, or you have a disilicate where you have 2 tetrahedra combined together, okay. And then you start forming cyclic or chain or sheet silicates or phyllosilicates, right. So, phyllosilicates are often common in CSH, but CSH is not entirely all sheet like, it may also contain some lower forms of silica like disilicates or cyclic silicates. So, because of this, when you actually evaluate CSH for silicon signals using NMR, you will actually get a combination of peaks, you will get a combination of different peaks. So, you need to identify which one corresponds to which type of silicate polymerization. And more interestingly, you can actually use this instrument to find out how does a pozzolanic cementitious mixture change with respect to time, because the initial pozzolanic state which brings in the amorphous silica will mostly have the Q0 type of peaks. Amorphous silica will mostly have Q0, Q1 type of peaks. As it becomes more and more organized in the CSH structure, it will start creating the higher forms of the silica like Q2 or Q3 for instance. So, there is an example given here of the silicon NMR spectrum of fly ash and how it is actually deconvoluted. So, here this is the actual signal that you are obtaining from your NMR spectroscopy. Now, why is this happening? Because all these peaks that are here are converging. So, there is an interference from all the peaks and ultimately it gives a summation which is given as one peak. So, what you need to do is now break this down into the individual peaks that you have in your system. Okay. So, again the peaks at all these locations are attributed to the starting vitreous material, that means the glassy material in the fly ash, and peak at minus 87.8 is attributed to crystalline mullite, and for minus 109 and beyond it is different crystalline silica phases in the fly ash. The more the crystalline phases, the greater the degree of coordination. So, you are shifting to higher negative values in the case of silica. So, there are a lot of ways in which such data can be interpreted, and because of this NMR remains a very powerful tool as far as cement paste analysis is concerned. One more aspect of NMR is the capability to measure moisture, because again water has hydrogen, and by doing a proton NMR you can actually determine the moisture states inside materials. And most of your moisture meters that are used in practice are either electrical based, because electrical properties are sensitive to the moisture content in porous materials, or they are NMR based. Okay. NMR happens to be a very useful technique for determining the amount of moisture present inside materials. So, generally proton NMR experiments can give information on hydrogen quantity or density by analyzing the amplitude of the signal. For instance, here on this picture, the amplitude of the NMR signal is plotted against the moisture content in wood. Okay, this is actually for wood, and you see here that with increasing moisture content you get a relatively good increase in the signal intensity. So, more the moisture content, the greater the amount of hydrogen protons that are present in the system. So, you get a greater intensity in the signal. Okay. And again hydrogen density is a function of overall water content. Again most NMR based moisture meters are measuring moisture in the systems by estimation of the density, hydrogen density in the system. Now, one more method of using NMR is to actually look at what happens when the atom starts relaxing. So, I told you that atom absorbs energy and becomes more unstable, but over time what will happen is it will take time to come back to its ground state. So, the time it takes for that relaxation to happen, for it to come back to the ground state, is another characteristic experiment that is used with NMR spectra. So, I am not covering that in our lecture here, but you may come across several research studies which have actually used the relaxation time for atoms to come back to their ground state, right, and that can also be used to actually characterize and quantify the type of species that are present inside your sample. So, NMR is a highly powerful technique to look at the coordination states of different atoms that are present in the system, right, and it gives primarily from cementitious materials viewpoint, it gives us an idea about what is the structure of the calcium silicate hydride that is forming in the system. Okay. So, with that we finish this chapter on spectroscopy techniques. There are tons of references available for spectroscopy techniques on the web, and there are several textbooks. What I have done is listed a few references which could be useful for you to actually look at more details of these techniques, and there is a lot of papers that you can read further to get an assessment of how these spectroscopy techniques can be applied for analysis of cementitious specimens. So, again here this is a very good paper, use of FTIR to study cementitious materials, and this one here by Grimmer and Zani and Suzani, that is actually a good book for NMR of cement based materials. If you want to look at a paper, this paper by Jog and Skipsted is a very commonly cited paper with respect to use of NMR for characterization of cementitious materials. So again, there is a lot of papers that you can actually look at with NMR. The more you read, the more confused you will become, because this technique is quite complicated. Okay. So although I have tried to simplify it in the best way possible, but I am sure that there is a lot of questions in your mind. Some of those questions may get answered by reading some of these papers. But please remember, the principle of spectroscopy techniques was quite similar across the range of techniques that we talked about. The techniques were based on the absorption of radiation, electromagnetic radiation at a given wavelength, which is characteristic of the type of phase or atom or molecule that is present in the system. Okay. While some radiations are at very low frequencies like radio frequency and so on, there are other radiations which are absorbed at higher frequencies like ultraviolet, or even greater than that obviously is X-ray and so on, which introduce some transitions within your phases which can be governed by identifying the locations of these transitions, and that leads you to analysis of the type of material that you are looking at. Okay. So spectroscopy has a common background, but the way in which the instrumentation is set up and the interpretation of the data is done is quite different. Okay. Alright, so with that we finish this chapter.